Now let us take a moment and not forget about audio surveillance, and V2K, voice to skull. Okay, let me just give you the simplified version first of audio surveillance and voice to skull. I posted yesterday about the 3 generators and 3 lasers. Sonic, health attack, well, we are going back there again. Further of all 3 generators are all connected, making a phase loop lock is made and ROF. Radio over fibers, this is going to be important today. Now a couple of radio frequency are added to the L1 1575.42 MHz using the BPSK modulation method. These will be used one will. With the sonic, health attacks outer area being electromagnetic and locked loop with microwaves, radiation, and other things, you basically have a radio station as a home. Anything said in the home can be heard by dialing in the ingested radio frequencies with L1 1575.42 MHz. Now voice to skull. A radio frequency is also added to L1 1575.42 MHz and becomes part of the sonic, health attack dome and phase locked loop, microwave radiation, which all contribute to microwave auditory effector hearing. This lets a person hear radio frequencies. Person near the target's home dials the ingested frequency into SDR computer and microphone, and you have voice to skull. Theodore W. Hansch and John L. Hall shared half of the 2005 Nobel Prize in Physics for contributions to the development of laser-based precision spectroscopy, including the use of the optical frequency comb. Within the laser, the different frequencies of light beat together to generate microwave radiation, very similar to the nonlinear mixing of paired signals widely used in audio through RF electronic systems. The light inside the laser cavity causes electrons to oscillate at microwave frequencies here, around 5 GHz, which are within the standard communications spectrum, including our Wi-Fi band. They were able to get the laser radio transmitter LRT arrangement to support energy radiation by redesigning the top contact of the laser and then using this internal oscillating current to drive an integrated dipole antenna that radiated it into free space. By modulating the laser current, they were able to directly encode an audio signal onto this carrier. Of course, every transmitter needs a receiver to be useful, and the receiver can have an architecture that differs radically from the transmitter, and even be ignorant of it. Think of the supergenerative, superheterodyne, zero-if, and software-defined radio SDR receiver approaches, none of which needs to resemble the topology of the signal source transmitter. To initially validate the optical to RF approach, they received the signal using a horn antenna, then filtered it and sent it to a SDR for demodulation. Electromagnetic cavity for rubidium atomsa. A waveguide frequency converter connecting rubidium-based quantum memories to the telecom C-band. I1/4. A cold cloud over 87 RB atoms confined in a GPS with rubidium atoms, magneto-optical trap MOTL 1575.42 MHz from GPS, serves as quantum memory for light. Inelastic scattering of a classical right pulse results in the emission of a Stokes photon, which heralds the presence of a collective spin excitation. A subsequent Reed pulse maps the atomic state onto an anti-Stokes photon. The retrieved light is sent to a PPLN waveguide, together with a strong pump at 1569 nanometer. The 780 nanometer photons are converted to 1552 nanometer by DFG. After conversion, residual pump light is blocked by means of a bandpass filter BF. The converted light is then coupled in a single-mode optical fiber. A fiber Bragg grating filters out the broadband noise generated by the pump. The non-classical nature of the storage, retrieval and conversion processes is probed by measuring the cross-correlation between Stokes and unconverted anti-Stokes photons B level scheme used for the DLCZ memory. The right pulse off resonantly couples the ground state GA to the excited level EA. A Stokes photon is emitted with probability of P, thus creating a single collective excitation to the storage state SA. During the retrieval process, a pulse resonant with the SAA-EA transition, red beam, collectively transfers back the atom to the initial state GA while emitting an anti-Stokes single photon in a well-defined spatio-temporal mode. The coherent manipulation of the frequency of single photons is an important requirement for future quantum network technologies. It allows, for instance, quantum systems emitting in a visible range to be connected to the telecommunication wavelengths, thus extending the communication distances. Here we report on quantum frequency conversion of memory-compatible narrow-bandwidth photons at 606 A nanometer to the telecom C-band at 1552 A nanometer. The 200 ANS long photons, compatible with praseodymium-based solid-state quantum memories, are frequency converted using a single-step difference frequency generation process in a periodically pooled lithium neobate waveguide. We characterize the noise processes involved in the conversion and, by applying strong spectral filtering of the noise, we demonstrate high signal-to-noise ratio conversion at a single photona. A copyright 2018 Optical Society of America.